Electrode potentials and cells. Electrochemical cell made from two different metals dipped in salt solutions of the own ions, made from two different metals dipped in salt solutions of the own ions, and connected by a wire, also known as external circuit. What happens in zinc/copper electrochemical cell? Zinc loses electron because it loses electron more easily than copper. Therefore, in the half cell, the zinc from the zinc electrode oxidized to form Zn2 plus aqueous, Zn2 plus aqueous ions, releasing electrons into external circuit. In the other half cell, same number of electrons taken from the external circuit, reducing the Cu2 plus ions to the copper atoms. Reactions that occur at each of the electrodes in an electrochemical cell are reversible. Electrons flow through the wire from more reactive metal to less reactive one. Salt bridge, you got your Zn solid, Zn2 plus aqueous. It loses electrons. Cu solid electrode, Cu2 plus aqueous, gains electrons. Salt bridge, there's your voltmeter in the middle. External circuit, your wire. There you go. Voltmeter in the external circuit shows voltage between two half cells, aka the cell potential. You can have half cells involving solutions of two aqueous ions of the same element. For example, Fe2 plus aqueous / Fe3 plus aqueous. Solutions are connected by a salt bridge, which is made from filter paper soaked in KNO3 aqueous. How half cells involve a solution of two aqueous ions of the same element happens on the surface of platinum electrode. Electrodes made of platinum as an inert metal therefore will react with the ions. Writing half equation for electrochemical cells, always reduction reaction in the forward direction and electrons on the left hand side. State key fact about when two half cells are joined together to make a cell, which direction each reaction goes and depends on how easily each metal loses electrons, aka is oxidized. Electropotentials measures how easily a metal is oxidized. Metal that's easy to oxidize measures how easy a metal is oxidized. Metal that's easy to oxidize has a very negative electropotential. Metal hard to oxidize has a less negative electropotential. There's always two reactions in electrochemical cell, one oxidation, one reduction, therefore it's going to always be redox in electrochemical cell. Oxidized half equation goes backwards, reduction half equation goes forwards. Electropotentials of half cell are measured against a standard hydrogen electrode. Cell potential, though, is affected by the condition, therefore standard conditions are used to measure electropotentials. Standard cell electrode potential of a half cell. The voltage measured under standard conditions when the half cell is connected to a standard hydrogen electrode. If the standard conditions are maintained, the reading on a voltmeter when a half cell is connected to standard hydrogen electrode is the standard electrode potential of the half cell, either E of the cell. Now, formula you have to memorize: E of the cell potential equals E reduced, cell reduced minus cell oxidized. So reduced minus oxidized. Electrochemical series, a list of standard electrode potentials for different electrochemical half cells. A list of standard electrode potentials for different electrochemical half cells. More positive electrode potentials mean that left-hand side substances are more easily reduced, right-hand side substances are more stable. We can use electrochemical series to calculate standard cell potential. More negative electropotentials means that right-hand side substances are more easily oxidized, left-hand side substances are more stable. So it's kind of the opposite. Positive electrode, left-hand side substances more easily reduced. Negative electrode, right-hand side substances are more easily oxidized. Positive electrode, right-hand side substances are more stable. Negative electrode, left-hand side substances are more stable. We can only use electrochemical series to calculate standard cell potential only when the two half cells are joined together. Reduced form, oxidized form, reduced form, oxidized form, reduced form. Things in different phases are separated by a vertical line. They're in different phases. Double vertical lines show a salt bridge. Key facts: half cell with a more negative potential is on the left. Always a half cell with a more negative potential is always on the left. Oxidized forms go in the middle. Reduced form, oxidized form, reduced form. Go in the center of the cell diagram. Reactions that take place in non-rechargeable batteries are difficult / impossible to reverse this way. Batteries are types of electrochemical cell which provides electricity we use to power watches / mobile phones. Some types of cells are rechargeable while others can only be used if they run out. Non-rechargeable batteries are cheaper than rechargeable ones, but as you can recharge / reuse rechargeable batteries, they're cheaper in the long run, last longer in the long run. Lithium batteries are rechargeable. Example: Lithium cells are used in mobile phones / laptops. A type of lithium cell is made up of lithium cobalt electrode, LiCO2, and a graphite electrode. Electrolyte is a lithium salt in organic solvent. How to recharge rechargeable batteries? A current is supplied to force electrons to flow in the opposite direction around the circuit. And reverses reaction. Current supplied to force electrons to flow in the opposite direction around the circuit and reverses reactions. A negative electrode, Li arrow Li plus plus E minus. A positive electrode, Li plus plus COO2 plus E minus to form Li plus COO2 square brackets minus charge.